Good afternoon, everyone. Welcome to today's seminar. Today, we are very happy to have Ignacio Reyes from Potsdam to talk about moving mirrors, page curves, and the bulk fields on AdS2. So, Ignacio, the floor is yours.
Hey, Dongsheng, thank you very much for the introduction. And thanks everyone for coming. I'm actually super happy to be here speaking. It's my turn to be on the other side of the room. So what I want to tell you about today is based mainly on this recent paper that I put up in the archive a couple of weeks ago. And also some work in progress. So here's the outline. I'm going to start with a very short review about a very well-known topic, the relation between moving mirrors and black holes. And I want to there emphasize what is the new ingredient that was put forward in this paper. And it's essentially a way of computing the reduced density matrix of the radiation of the fields produced by the moving mirror. Then the main part of the talk will concern mirrors in two-dimensional flat space. I'm going to tell you a little bit about how you actually do the calculation. So for free theories, you can use these exact complex methods, namely the method of the resolvent. And then I'm going to show you some results about the Renyi entropies. I'll tell you how you can obtain a page curve and discuss in detail the issue of unitarity in this system. And then I'm going to talk a little bit about modular flow. And finally, once we understand the results in flat space, I'm going to talk a little bit about how one can generalize this to curved spacetimes, and in particular, some results that you can find in AdS2 and how that affects or brings new ingredients to think about the physics of these so-called quantum extremal surfaces. And we're going to close with some outlook. Okay, so let's talk about moving mirrors and black holes. And by the way, as everyone knows in these seminars, just interrupt me at any time in case you have comments or questions. And thanks to all of you that kept your cameras on. It's actually cool to see people. Okay, so how do we define a mirror? Well, that is simply a codimension one surface in space-time where we impose reflecting boundary conditions on the fields. Now, something that is very well known to probably most in the audience is that if you now look at quantum field theory and you look at a perfectly reflecting mirror, if you wiggle this mirror, you accelerate it, the mirror is going to produce radiation. And this is nothing but a sort of dynamical version of the Casimir effect that we all know from quantum field theory. So of course, in the case of, so what is the connection to black holes? Of course, in the case of black hole physics, what you have is some equation of, there's some properties of the collapsing matter that forms the black hole. And then there's the equation of general relativity, and the interplay between these two things they fix the structure of a space-time. And on top of that, what Hawking did was the quantum field theory, and then looking at the black hole evaporation. Now, in the case of the moving mirrors, one has in principle a larger degree of freedom because we can look at arbitrary or almost arbitrary, with some constraints, arbitrary trajectories for the mirrors, which produce all kinds of radiations. So it's only a particular class of trajectories that will mimic a black hole evaporation. Actually, one can find an exact mapping between the certain accelerating mirrors and black holes in higher dimensions. Now, so you can reproduce essentially the same physics as in the Hawking effect, but the cool thing is that this setup is much simpler because you simply need to deal with quantum fields in flat space-time. Now, traditionally, there have been, I think, two main two main approaches or strategies to deal with these problems. The first one is to essentially, so first of all, here on the left, we have the Penrose diagram of flat space in 2 dimensions. And here I'm depicting 2 different mirrors which behave very differently in the asymptotic future. We're going to talk more about this later. So the fields, the incoming modes or the left movers here, once they reach the boundary, they're simply reflected and become right moving modes. So the first strategy to tackle these problems was to essentially look at the properties of the asymptotic future of the outgoing state. And this is very much what Hawking did in his original derivation, right? Computing the Bogoliubov coefficients and so on. And of course, there's a huge number of references. This is a very big field. But here I'm just giving one of the very important references. So there was a series of beautiful papers by Fulling and Davis where they really pioneered this thing of doing the map from Hawking's calculation to these moving mirrors in 2 dimensions. But there you really concentrate on the information that is contained in this sort of region of space-time. Then there's a second approach, which is essentially to use symmetries, and in particular conformal symmetry, to try to do some computations. So here you could do something like, for example, choose some Cauchy slice and compute, for instance, the entanglement entropy. That's typically what people are looking at. But because you want to use conformal symmetry to do the calculation, this restricts the class of questions you can ask. So in particular, if you use what we now call boundary conformal field theory techniques, typically what you're able to calculate is, say, the entanglement entropy of a semi-infinite interval. And the reason is because if you think about the replica trick, you really need to take one of the points. So here, the right point, you really need to take it to infinity, because once you do the replica trick and you use essentially the method of images, you're going to have to compute a 2-point function. And that is fixed by conformal symmetry. But if you use the finite interval, this would include higher point functions, which are not determined, as we know very well, by the Virasoro algebra. So typically, this is the situation where to which you're restricted to. And there was this very early paper. Of course, there's many more, as I said. And I wanted to point out here a very recent paper, actually, by the group from Kyoto, where they went beyond this. So actually, they looked at holographic CFTs, and then you can really use AdS to do the computation, but it's essentially going in the same direction. So a third approach, which is the one that I was using in this recent paper, is essentially to just compute the reduced density matrix on some arbitrary number of intervals on whatever Cauchy slice we want. So this is really the picture that we're going to have in mind. I'm not restricted to either the asymptotic future or these semi-infinite intervals, but rather I just want an arbitrary set of intervals. And the reason why I want to do this is because, not just because you can, but because really the reduced density matrix contains all the information about a quantum system. There is no other set of data that you would want to have. The reduced density matrix is the state of the system. And the fact that you can consider disjoint regions is very convenient when you want to ask questions about what are the correlations between subsystems of the radiation, which is something we're going to talk about later, and is quite relevant to the discussion of black hole evaporation. So this is really the thing I wanted to capture in this project. Okay, so what are the kind of observables or the things we want to compute? Well, there's a long list. Here I'm just putting some of them. A very important thing are going to be the Renyi entropies. These, as probably everyone here knows, are just a 1 parameter family of generalizations of the entanglement entropy, which carry an index n. such that in a certain limit, they become the entanglement entropy. Other things that you might be interested or that are very interesting to look at are, for example, relative entropy. I'm not going to talk about relative entropy very much today. What I will talk a little bit about is going to be the modular Hamiltonian and modular flow. So the modular Hamiltonian is, by definition, essentially the log of the reduced density matrix. And that Hamiltonian produces a flow. That's what's called modular flow, which is essentially time evolution using the modular Hamiltonian itself. Another quantity that you can compute once you have the Renyi entropies or the entanglement entropies is mutual information. And actually, I'm going to emphasize this later on because I think it's something that has been rather overlooked in these discussions, and I think it's very interesting. Of course, there's many other measures or probes for entanglement in general, but these are just some of them. Okay, so before going back to the physics of the mirrors and telling you what the results are, I'm going to make a short detour. I'm just going to give you a very quick overview of how you actually do the calculations. My talk is not going to be focused on these tools, but I just want to give you a glimpse of how this works. So the idea is that here I'm going to restrict strictly to free theories in 2 dimensions, because there you can apply in a very nice way this so-called method of the resolvent. Now, the seed of this thing was really the form of the density matrix for Gaussian states, of the reduced density matrix for Gaussian states, was known a very long time ago. This was already discussed in the 70s. But I think it was not until the paper by Cassini and Huerta, a bit more than 10 years ago, that really they showed how to use these things to do analytic explicit computations. So let me give you a very simple example. Suppose we want to compute the Renyi entropies, which are by definition given by this thing. It involves the traces of the powers of the density matrix. So if I say Renyi entropies, probably a lot of you are going to immediately think about the replica trick. The point here, and one of the cool things about the free theories, is that you don't need to use the replica trick. We can compute these things by definition. That is, you can, because the higher, the endpoint functions are, you can reduce them using Wick's theorem and bring them to the 2-point function for free theories. Everything depends on the correlation function. So once you have the correlation function, you can basically compute everything else. So if you wanted to compute, for example, this log, the trace of rho to the n, you can rewrite that in terms of the correlation function, seen as an operator, as a matrix. You compute its log, and then you simply take the trace. So this is computing things by definition. You don't need to use the replica trick. Of course, you could use the replica trick, but this is a very direct way. So then the question is, well, how do you do this computation? And this becomes a standard question in holomorphic functional calculus. So the idea is that you want to define the function of an operator. So under certain conditions, which I'm not going to be very precise here, what you do is you basically use Cauchy's integral formula. So if lambda was an eigenvalue of the operator G, then this formula would be sort of satisfied trivially if gamma is a contour that wraps around the eigenvalue G. Now, you can promote that equation for each eigenvalue into an equation for the operator itself. And so you can define the function of this operator as given by this integral, as long as gamma, the contour of integration, really encircles, contains the entire spectrum of the operator. So then it's a matter of choice, depending on which quantity you want to compute. You simply replace your function f there, and you do a contour integral. Now, of course, the really challenging thing here is to compute this inverse over here. So this pole, 1 over lambda times the identity minus g, this is known as the resolvent, and is defined by this equation over here. So it's the inverse of this operator here. And basically, that's what you have to do. You have to solve for this resolvent. So what we did in some earlier papers was something very simple. I don't want to sort of dwell too long on this, but basically what you do is if you make there's a strategy, there's a recipe to solve this problem. If you separate the resolvent into the identity plus some other function that we're calling f here, this equation, the equation that defines the resolvent, the equation you want to solve, becomes, now if you simply insert this over here, this becomes an equation for f rather than r. And if you introduce the terms, you simply get this. So this equation here that I'm writing in a very abstract way, what it literally means is this equation over here. So as I said before, G depends on two space-time points. So it's can think of it as an infinite dimensional matrix. And now f, the function we're looking for, has the same thing. And this multiplication here is essentially like a convolution between f and g. So this is an integral equation that you're supposed to solve. And it has singularities because g, the correlation function, diverges when the 2 points become very close. That's just UV physics. So what we did, very much inspired by this paper, what we did 2 years ago was to find a recipe of really how to solve this equation. And the recipe is by recasting this as yet another residue problem in the complex plane that has nothing to do with the previous complex plane that I told you about. I don't want to go very much into the details of this. So basically, you try to recast this equation, the one that you want to solve, as a contour equation. So you're looking for a holomorphic function in the complex plane such that it has zero residue around the entangling region V. And under a list, so there's a list of requirements under which this equation, this contour integral equation, becomes this equation over here. And those requirements are given here on the right, and they correspond to the figure on the left. So the idea is that if you have your entangling region of interest, V, you're requiring that the integral of the combination, the product of these two functions along this contour over here vanishes. And if you use some simple residue analysis, you're able to rewrite, so deform that contour in essentially a sum of 3 terms, 2 isolated poles. And you require that the function here on the integral must have a branch cut of a very specific kind, namely that if you integrate just below and then you integrate just above, the sum of these 2 terms in the contour integral must give you the regular integral in the original equation. So there's a set of conditions that you can impose. This is a very well-defined mathematical problem, and it has a unique solution. Once you find that solution, you just replace it back into the resolvent and you solve the problem. So you find this function f, you go back, you introduce it into the resolvent, and then you plug it back into the contour equation. Now, which f do you have to choose? This little f? Well, it depends. If we go back one more slide, it depends on which function you want to compute. Each of these functions corresponds to a different little f. And that's how this thing goes. Okay. Okay, are there any questions till there? Okay.
So is it equivalent to this Gaussian method that you mentioned by Peschel, or is the
Yes,
somehow?
Yes, yeah. This comes from there. Yeah.
But it's somehow like it's faster to just compute this way than computing the covariance matrix or something. Or?
Well, essentially what we're borrowing here from Peschel is the fact that where did I write it? Here. So that this actually, I don't have, this is going to appear much later in the talk, but the thing we're borrowing from Peschel is that the modular Hamiltonian for a Gaussian state is going to take a specific form with a specific kernel. And what he gives is the form of this kernel as a function of the correlator. And then once you have that, you just run this machinery and you get everything for free once you have the resolvent. But yeah, I'm sure there's, I mean, you could also use explicitly what he was doing, but I wouldn't know which exactly is faster or anything. It's just that I'm very familiar with this one. Okay, so these are the math tools that you have to use to eventually do the computation. So now let's go back to the physics and look at the specific problem in question. So let's look at the fermions in these mirrors. So here's the specific setup. If we look for a second, the figure on the right. So first of all, the mirror is parameterized by a function g. So this is the trajectory of the mirror in null coordinates. And the physical region is everything to the right of the mirror by convention. So the idea is that to solve this problem, you want to first foliate space-time with certain Cauchy slices. And in every Cauchy slice, you want to define a global density matrix. So that's the density matrix living in the entire slice. And that's the density matrix you want to reduce to some arbitrary set of disjoint regions. Here I'm just drawing two, what I'm calling V. And then we want to track these regions as they evolve in time. So this is the standard space-time diagram. I'm going to label the endpoints generically in the talk as left one's A and the right one's B. So if there was no mirror, if there were no boundary conditions, if you look at the plane, for example, then the left and right movers would be completely decoupled, and you could simply solve for one sector, and then the same thing would apply to the other sector. And in that case, if we now think about the 2-point function, the 2-point function is now a matrix. So that's simply because this is the 2-point function of the Dirac field. Now, again, if you're on the plane and there's no boundary conditions, then the cross terms would vanish because there would be no correlations between the left movers and the right movers. The novelty here is that the mirror tells you how these two sectors are correlated. So these off-diagonal terms do not vanish. That's the main new thing. There's also the fact that the diagonal terms also change depending on the trajectory of the mirror. But the key fact is that now the two chiralities become entangled. Now, because the mirror in general is going to be wiggling and accelerating and moving in some arbitrary way, this means that there will be an exchange of energy and momentum into the system or out of the system. So energy and momentum can be either extracted or injected into the system from the boundary. So typically, for example, in BCFT, what you normally want to do is to require that is no transfer of energy or momentum along the boundary. That defines a set of boundary states, etc. And there you require that this parallel perpendicular component of the stress tensor vanishes at the boundary. Of course, here it's not going to vanish, and it's rather going to be given by essentially the anomaly, where G again is the profile of the boundary of the mirror.
So Ignacio, can I have a question, please?
Sure.
So I mean, if you restrict yourself to a class of Gaussian states, right? The vacuum, I guess, is going to be a Gaussian state, but there's going to be also many other Gaussian states that you can consider, right? So what assumption do you make at the Cauchy slice at path infinity regarding the state here?
Okay, that's a very good question, actually. So what I did explicitly in the paper was to restrict to thermal states. So all the states I'm going to look at are going to have the form e to the minus beta h, where h is the physical Hamiltonian. Now, most of what I'm doing applies for generic, or the strategy that I'm using applies for generic Gaussian states. The problem is that
to understand it better, you have like the Hamiltonian on a half line, and you consider a state that is a thermal state with respect to the Hamiltonian on the half line. This is what you're doing.
Yeah.
In the infinite path, and then you just let it evolve, taking into account the mirror.
Yeah.
I see.
Now you could do this for more general Gaussian states. There are Gaussian states is a huge class of states. You could consider all kinds of non-local interactions, and you can run this machinery. But the problem is that the solution for the resolvent is not known in general. So.
But from the point of view of a Gaussian calculation, okay, I mean, maybe that's not the case, but you know, like thinking about it as, you know, putting this thing on the lattice, etc. I mean, it should be doable with other Gaussian states numerically.
Yeah. Numerically, certainly you can do it. I think so the thing that you can probably not do in general, or it's very hard, maybe there's a solution, it's just that it hasn't been worked out, is that if you look at an arbitrary Gaussian state, this 2-point function is going to be some very complicated thing. Maybe you have an explicit formula, but it's going to be very complicated. And solving this equation is going to be extremely hard.
I see. But like from numerical perspective, like these equations don't appear there explicitly, right? Like you just have covariance matrix and you apply some simplex.
Yeah. No, you can probably do it. Yeah. Now, if someone would find an analytic formula, an analytic solution for generic arbitrary state, this would be, I guess, pretty cool actually. Just the solutions are known for thermal states. Okay, good. Thanks. Okay, so this is the setup. So here's a first result. Applying. Sorry. Go ahead.
One more question. So, how essential for you was it that these are free fermions? Like, if you had free bosons, like, would you be able to do the same?
Yeah. Well, in principle, you can do the same, but in practice, it's very hard. Because essentially the density matrix for the free scalar for the currents is just a very nasty operator. The modular Hamiltonian is completely non-local. Computing the entropies of multiple intervals is super hard. So you can run the same machinery, but the calculation just becomes much more difficult.
No, good. Okay, thanks.
Okay, so with all the tools that I told you until now, here's one important result that you can find explicitly. So everything that I put in the paper is valid for an arbitrary set of intervals, but here I'm just, to illustrate it, I'm just giving you the result for a single interval. So here are the Renyi entropies of a single interval, AB, for the case where the moving mirror has an arbitrary boundary, given by a function g. So here's the result. First, all the dependence on the index n appears as an overall factor in front. And then you get this usual log behavior. The first, I kind of isolated this first term in this expression. This is what most people will recognize as the universal result. That is one contribution to the Renyi entropies. But then there are other terms which depend on the mirrors, G. The important thing to point out here, more than the explicit form, is the dependence on the mirror. So the Renyi entropies depend on the mirror only through two numbers, the position and the velocity, so G and G prime, evaluated at the null projections of the boundary points, of the endpoints of the region. Okay, so this is what I'm depicting here with these lines and these red intervals here. It depends only on what the mirror is doing there, so its position and first derivative at those points. And all the remaining history, it doesn't matter what the mirror does anywhere else. So this means that if you have considered two times, say you have the system at t1 and then you look at it later time t2. If the position and velocity of the mirror at those projections at t1 and t2 are identical, this means that the Renyi entropies of these two states are going to be identical. And if all the Renyi entropies are the same, this means that the density matrix, the two density matrices have the same entanglement spectrum, the same eigenvalues, and this means that there's a unitary transformation relating them. So this is not only consistent with unitarity, this is the definition of unitarity, more or less, I guess. So I think I wanted to emphasize this point because due to all of the discussion about, in the last couple of years of a black hole evaporation, what people focus mostly on, because it's what you can calculate actually, are entanglement entropies. But getting a page curve for the entanglement entropy alone does not, of course, guarantee unitarity. It's just consistent with unitarity. It doesn't violate it. But what we should actually expect, hopefully in the future, is that from black hole evaporation, is that we should get something like this. We should get a page curve for every Renyi entropy. Yeah, so I think that's an important remark. And here also, I wanted to mention again, this recent paper by the group from Kyoto is also looking at related stuff. Of course, they were not looking at the Renyi entropies because they were doing holography, but it's very interesting and there's many connections to what I was doing here.
So can you do holographically Renyi entropies or like similar entropies via Shidong's calculation?
Good. I would tell you yes, but good luck with getting into. I think this is very challenging. I mean, this hasn't even done for static configurations. So I think it's very interesting, but it's very hard. Maybe in 2 dimensions you can do something. I don't know. And I think that's a very important question. So what I just said is valid for an arbitrary mirror. So let's look at some examples. So essentially what focused here is if we look again at the Penrose diagram, I'm just depicting 2 different mirrors that behave very differently in the asymptotic future. So essentially, and this is related to Michael's question, so the incoming state is what you define here on null past infinity over here. And there I'm going to scatter. So I'm going to, the incoming state is going to be an equilibrium state at some finite temperature beta. And then that's going to produce through the mirror some outgoing state in the asymptotic future. I focused here mainly on Cauchy slices of constant time, but this is, you can easily generalize it. And one thing to notice is that the fact that the Renyi entropies between 2 states are identical doesn't mean that the 2 states are the same. And generically, the outgoing state is going to be very different from the incoming state, even if the Renyi entropies match. And that's also, I think, what we would expect from black hole evaporation, right? There's a matter that collapses and then the black hole evaporates, but the final state of the matter doesn't need to be the initial state. It doesn't need to be like a cyclic process or something like this. And lastly, this, just for technical reasons, one usually requires that the mirror is static in the asymptotic past so that you can define vacuum and so on as incoming states. Okay, so what are some very concrete examples now? The first one is, of course, the static mirror. This is not doing anything special. Because it is static, you can impose, or it is consistent with conformal boundary conditions. So there you compute this exchange of energy with the outside region, and this is, of course, 0. And here you can compute the Renyi entropies on the right half plane, and this is the result that you get. basically it has two components. The first one is the standard universal result that you would get if you don't have a boundary. And the second term is much more interesting. This second term, which is written here as a function of the ratio between the two endpoints, is what you get is really the contribution coming from the boundary. And this has a set of nice properties. So this extra term, first of all, it's negative. It's not so obvious from here, but it's very easy to convince yourself that the thing inside the log is smaller than 1. So this second contribution is always negative. It goes to 0 when you take r going to 1. So that means that a and b, that means that the interval becomes very small. This term vanishes, and that makes perfect sense because that means that the interval is so small that you're very far away from the boundary. Effectively, you don't see the boundary effect. And finally, if you take this ratio to be very large, it seems to go to -infinity, but actually you should stop at some point, because at some point you're messing up with the UV cutoff. But essentially, the important thing is it's negative, so it lowers the entropy. Now, this is in perfect agreement with the same result found in this previous paper, where they looked essentially at a single interval. Now, the fact that this term is negative is actually, it's the monogamy of entanglement in action, really. So what's happening here is that because now the two chiralities are entangled between each other, these two fields, they cannot be as entangled with the rest of the system as they were in the no boundary case. And that's a sort of intuitive way of understanding why the boundary actually lowers the entropy of the system. And as we'll see, this has some consequences in AdS as well. So basically here, one can sort of classify this result in the following way. So here there are two important states that we can distinguish with this calculation. If you have no boundary, then essentially the state that you would be considering is the tensor product of some left movers and some right movers put at the same temperature. This state over here, of course, when the temperature goes to 0, I did the calculation of finite temperature, but I'm just showing here for 0 temperature. This state over here has no quantum correlations between the two sectors. It has a classical correlation between the two chiralities because you're putting the two states at the same temperature by hand. This is the result that is universal, fixed by conformal symmetry, etc. The extra term that you get is when you consider a different state, this one over here, where H plus and H minus, the two Hamiltonians for the two different sectors, do not commute because of the boundary conditions. And here there are quantum correlations between the two chiralities. That's the key difference between these two states. And the second state, the one on the right-hand side, is the one I was focusing essentially in this paper. And this is not universal because it depends on the higher point functions and so on. Okay, a second interesting example is if you consider a mirror that is accelerating uniformly. So again, it starts static in the far past. It starts as a state that I just talked about. So there's these quantum correlations between the two chiralities, and the entropy is given essentially by that same thing that I showed you before. But now it starts accelerating at a fixed rate. It becomes null, of course, in the future. And what you can show, I'm not showing the calculation here, but I'm just telling you what happens, is that in the far future, the state that you get is exactly this tensor product that I was talking about before, which has no correlations between the two chiralities and has the entropy, which is given simply by the first term. Now, of course, as we said, this term over here, the second term, lowers the entropy. This means that the entropy of the entire system grew in time, right? Because you lost this negative term because of the motion of the mirror. This means that, and this is of course one example of non-unitarity. The entropy of the final system is larger than the entropy of the initial system. But what is kind of cool in this example is that this mirror exactly erases the quantum correlations between the two chiralities in the initial state and produces this tensor product in the future. And it's a very simple example of a non-unitary process. Okay, another example, and this is more closely related to black holes, is this sort of the Hawking state. So that means that the state we throw in from the past is the vacuum, and then you find the specific trajectory that renders the final state as a thermal state, as an exact thermal state in the asymptotic future, of course, at some outgoing temperature. If you do this, of course, what you get as the outgoing state is a thermal state. This is very similar to Hawking's example. But here, one should point out that this mirror does not exactly erase the correlations as the one before. So it's not true that every non-unitary mirror is going to do this trick. It's just a very special class. And of course, if you can actually do the opposite, you can typically, when we think about black holes, we think about sending in the vacuum and getting out a thermal state, but you can do the opposite by simply using the inverse function of this mirror. You can throw in a thermal state and get the vacuum as the outgoing state. So it still violates unitarity. It's just like a inverse violation. Okay, and this is the state that you can really map into the 3+1, Hawking calculation. Okay, so once we understand how this thing works, one key question is to explain how to define and how to get a page curve. So here, by page curve, what could follow simply the Renyi entropies, as I did before, of the radiation. But actually, I think the reason I don't like this approach, which is what actually is the most dominating one, is that, first of all, Renyi entropies don't exist. They're all UV divergent. They're not well defined. And moreover, if you want to capture the entropy associated to the very, very early radiation, say in this example in the figure on the right, you're going to have to send the right point of that interval very far, all the way to spatial infinity. And that is generically going to introduce yet another divergence, because you're going to send this point to infinity. So instead of doing that, I think a much better idea is to use mutual information. So, which is defined, as we all know. So the idea is that in the Penrose diagram here, I want to compute the mutual information between an interval that stays closer to the mirror and an interval that goes all the way from some finite point all the way to infinity. So this, by definition, is computing the correlations between the very late radiation and the very early radiation. And it's well defined, it's UV finite, it's completely finite. So I think this is a much better quantity to look at. And you can plot this thing, and here I'm giving you a very simple example. This, the yellow line corresponds to a unitary mirror. So when you plot this, these correlations between the early and the late radiation, you'll see that the mutual information does something, but eventually returns to its original value. Whereas for this other trajectory here, which I chose as the Hawking one, it doesn't. It starts at some value, and then the final value of the mutual information is lower. So this means that correlations were lost in the process, or if formation was lost, if you want. Okay. Now this difference, the difference between unitarity, which is this line over here, and non-unitarity, you can measure this difference. And this gives you a way to really sort of quantify the violation of unitarity. And you can do this calculation actually analytically. It's quite nice. It has a specific form, but just for time constraints, I'm not going to stay here. But if someone is interested, I'm happy to go back here later. So
Ignacio, can I ask a
Sure.
clarifying question? So yeah, so non-unitarity comes about because there's a part of null infinity that you can escape to, right? Like this is the reason for
essentially, yeah.
Good. And the other question is, would you see this non-unitary behavior for? Yeah, you claim basically that you would be able to see this non-unitary behavior for any two-interval configuration, provided that you wait for long enough times, right?
Well, yeah. I mean, I think you have
This is a statement of asymptotics, right?
Yeah. So you want to wait a long time because you want to, you want to define the end state. For example, for this line, the yellow one, of course, you can have an oscillating mutual information for a short time, but you need to be long enough such that the states that you have a steady state, and then you can really compare things.
And is there some physics in this oscillation?
Yes, but I wouldn't like to get into that right now, but it's related to this, essentially just propagation of light rays intersecting boundaries of these regions.
Okay. Yeah, thanks.
Thanks.
Can I ask a question?
Sure.
So where in the calculation you were describing earlier in terms of resolvents is the time of the the Cauchy slice sigma? Where is that appearing?
Yeah, so it's in the 2-point function.
Okay.
Yeah.
Okay, thank you.
Yeah, okay. Yeah, that's it. Okay. So the resolvent depends on two spacetime points, and those spacetime points involve a time. Okay. So let me jump to modular flow. The last thing about flat space. And again, I'm going to be quite schematic here. So as many of you know, modular flow means you calculate modular Hamiltonian, and then you do time evolution of a certain operator. You just sandwich it with time evolution with the modular Hamiltonian itself. And in general, this is a very complicated operation. That's why there's basically a handful of results out there. And basically, what you get for this example, this is a complicated calculation, but just a very rough idea is here. So suppose we flow the fermion operator itself. So this means it's the operator evaluated at some point, fixed point x, and we flow the field of a given chirality I. What you get as a result is a sum of different terms. Let me forget about the sum for a second. So the modular flow is taking the field at x of chirality I, so of a given chirality, it's transforming it into two terms, one term of the same chirality and the other term of the opposite chirality. And it's sending those points from x to some other points, which I'm labeling y here, and it comes with certain coefficients. Now there's a pair of points or a pair of operators in each interval. So that explains the figure below. So suppose we took this black dot here is x. Suppose you take the operator there, you do modular flow. The result is going to be that you're going to get 4 terms. So it's 2 chiralities per interval. Here, the points are denoted by y1, y2. These are the same chiralities. And y-1, y-2 correspond to the operators with the opposite chirality. And the details are not very important, but what I wanted to point out is that those terms of the same chirality are very similar to the solutions found originally by Cassini and Huerta. They're not the same, but they're similar. And it's really those terms that involve exchanging chirality that are the new terms. And yeah, so you get 1 point per interval per chirality. And the way how you find those points is solving these, finding the roots of these complicated functions, which we don't need to discuss so much. But for the case of a single interval, this was also worked out in this earlier paper.
Sorry, Ignacio, the lines are supposed to represent the modular flow associated with the different chiralities, or what are these?
Yeah, okay, so what do these lines represent? So these points, the points to which the operators are mapped, these depend on time. Of course, they depend on modular time. That's the relevant parameter here. So the idea is that in general, these are solutions to some complicated transcendental equations, but how do you find them in practice? Well, you have to plot a certain function. So let's focus on the blue lines for now. That's the solutions with the same chirality. You plot a function, and wherever that function intersects the axis, that is where the modular flow is sending you. Now, the height of how does modular time act on this plot? It shifts this curve by an amount tau. So when you start time evolving, these blue lines are going to start moving, and the roots are going to move correspondingly, and that is really modular evolution on the slice.
Okay, thanks.
Yeah, sorry, it's not very intuitive, but maybe I chose the wrong plot. But thanks for the question. Okay, so just to finish the idea here, the mirrors don't change qualitatively the locality properties. That is, if there was no complete non-locality, say in the static boundary, you cannot produce like a qualitatively new form of non-locality by just wiggling a mirror. Now, this story about the modular flow is, I think, something that would be very interesting to look at for the case of black holes. So the last thing I want to point out is what can you say about curved spaces, and in particular AdS2. So I just considered fermions on AdS2, and AdS comes with an asymptotic boundary. So the idea is that now the asymptotic boundary is going to be the mirror. I'm going to impose reflecting boundary conditions on the fields in AdS. And I'm going to make use of the fact that AdS is related to flat space to the right half plane by a Weyl rescaling. So here again, there's a choice we can make. We could, the state I'm interested in is the one in which there's this correlation between the two chiralities. You could, of course, choose a state in AdS where there is no correlation. So there's this tensor probe, and this is actually the state that was considered in these island papers by these authors to do their calculations. So I just want to compare what you get in these two cases. So the idea here is that the conformal boundary is at x equals 0. And in principle, we can, given what we did, we can choose an arbitrary set of intervals in AdS. These are really bulk fields. This is not the CFT on the boundary. This is bulk fields. But if you want to talk about RT, if you want to think about the Ryu-Takanagi formula or its generalization to 2 dimensions, what you want to do is to really anchor one endpoint to the boundary. So that's the example I'm going to be giving. Now, if you think about these two states have the same energy because the energy just separates into contributions coming from left and right movers. So a measurement of the energy can never distinguish these two states. You have to measure entanglement, and that you do by computing entropies. So basically, because I'm looking at the static portion of AdS, you can impose conformal boundary conditions. There's no exchange of energy with the exterior, and there you can use the tools of the replica trick, namely that the Renyi entropies are given by these correlation functions of the twist operators now on AdS. And because these are primary operators, and because AdS is simply a Weyl rescaling of flat space, this gives us for free essentially the Renyi entropies on AdS2 with reflecting boundary conditions, given that we already computed them in the right half plane. So we can just take the results that we did on the plane on flat space and find the results on AdS2. And again, one very simple example, if you take the vacuum, again, I'm comparing these two states. So the line above, so here I'm plotting the entropy as a function again of the ratio between the two endpoints now in AdS. And here I just wanted to illustrate the difference between the state that has no correlations and the state that does have correlations. The red one is the one in which there's no correlations, and there the entropy really diverges when you take this ratio to be very large. When you go very deep into the AdS bulk, the entropy is very large, diverges, whereas it becomes a constant if you look at this boundary state. So this is effect that this difference is something you can really see at low temperatures, because at high temperatures you will need to look at the black hole and so on. But the point is that the form for the entropy becomes extensive, and then these two states are essentially the same. So how do you apply that into some interesting quantity? Well, this has an implication into these quantum extremal surfaces, because there's this, well, by now very well known a formula of the generalized entropy, where let's say we're doing AdS-CFT, and then the generalized entropy is given by the area of the RT surface plus the entropy of the bulk fields. In this case, it's going to be the bulk fermions. And then the quantum extremal surface is defined as the extremum of that functional. Now, because in 2 dimensions gravity is very simple, actually what people do is to consider a bit more exotic forms of gravity. In this case, I'm looking at JT gravity, so it's essentially just dilaton gravity. In that case, you replace the area term by the value of the dilaton at the endpoint. So the value of the dilaton at this right point here. And the dilaton has a specific form if you look, for example, at the vacuum solution. So on top of this thing, you can put the fermions in these special states and look for the quantum extremal surfaces. So you take that point B, you do this minimization process, and you can compare what you get between these two states. And on the left is the result from this well-known paper. If you take the decoupled state, you're going to get a finite location for the quantum extremal surface. And this was used to argue that there were islands outside the horizon and so on. But if you take this state with quantum correlations, you find that actually it's very simple to see that the only solution is not really an extremum, it's more like a minimum, and it goes all the way to infinity. So there's no non-trivial location of the island. It's always going all the way to the Poincare horizon. And again, this thing is just a consequence of the monogamy of entanglement.
So, do you want to finish, or can I ask a question?
Yes. Can I finish this one?
Yeah, sure.
Thanks. But this is, I think, the last thing I want to actually say. So what I just showed you was that you can compute, for example, entropies, Renyi entropies in AdS2, and this is super nice. You can do it for the black hole, actually. It's just, well, I showed it here for the vacuum. But an interesting question, and I think a more interesting question, is whether you can actually do this for modular flow, for the density matrix itself. There's been a lot of talk about modular flow in the book and the boundary in AdS, and this is a long discussion. And what I want to point out is that simply that this does not work for modular flow. So if you recall, the modular Hamiltonian is simply the log of the density matrix. And for Gaussian states, it just takes this form. Going back to Pablo's question, So the key thing is that there's this kernel in the modular Hamiltonian, and that kernel is given by a certain function of the correlator. It's given by this. And although the 2-point functions transform nicely from the plane, from flat space to AdS2, simply by the factors given by the Weyl rescaling, you see directly from this formula, because it depends in this way, the correlator, the kernel does not transform in a simple way under Weyl rescaling. So in other words, the resolvent in, say, AdS2 or some other Weyl rescaled metric, you cannot simply obtain in a very easy way using conformal transfer or using Weyl rescalings. So you really have to do the calculation from scratch. So what we're actually missing is the resolvent in curved spacetimes calculated from first principles. And this is actually a work in progress that I think is going to be a very interesting story. So, okay, I'll just leave this with a summary. I told you how to compute the density matrix for these moving mirrors. This gives you some very nice, powerful tools to address non-universal questions. The mutual information, I think, is a better way of posing the information paradox. And for the free fermion case, you can really guarantee unitarity. I mean, you can study the conditions under which unitarity is actually achieved. And I told you how to do certain class of calculations on AdS2. And then as an outlook, I think there's many interesting things to explore. Like, as I said, finding the resolvent in curved spacetimes, looking at putting some degrees of freedom on the mirror, because the mirror that I put was simply a line that was kind of God-given. We could look at massive fields in the bulk. We could apply these techniques to actually black holes. And then there's some longer shots about, for example, everything that I said was about time-like or light-like boundaries, but what about space-like boundaries, like the black hole singularity, etc. But with that, I'm going to end, and thank you very much.
Thanks, Ignacio, for the very nice talk. I think there should be many questions, so let's start. Anyone would like to ask the first question?
I can try if there are no other people. So can you please go back to the islands outside horizon slide? Yeah, thanks. So so it seems that like there are two calculations. One from the original paper with an island outside the horizon, like the other one that you did or you're doing without island. And then the question is like, does island outside the horizon require fine-tuning? Okay, can your framework make a generic statement, at least in the realm of Gaussian states?
Yeah, no, I would say no, it does not require fine-tuning, because I didn't show it here, but okay, I didn't mean to be misleading. Huh? What I'm showing here is the result at 0 temperature. That means the black hole is extremal, right? And then you have these two states, and in one case you find a sort of a quantum extremal surface at a finite location, and the other one just goes all the way to the horizon. If you do the same calculation at finite temperature, these two results change. So now, of course, the island on the left-hand side, or the quantum extremal surface on the left-hand side, moves because it depends on the temperature. It's going to be located at a different point. But also the state on the right will lead to some quantum extremal surface that is not going to be exactly at the horizon. But these two quantum extremal surfaces are going to be still different. So I would say, but this is not surprising, right? I mean, it's just the fact that we're looking at different states. The black hole really was somehow the matter that collapsed or something like this gave rise to two different states.
Yeah, thanks.
Maybe I could ask a question. So I was thinking in the you mentioned this paper of Davis and Fulin, and they talked about so there are some particles actually they don't really need to carry energy, right? And
yeah. Okay, good. I didn't mention this, but sorry. Here. So
yeah, so actually my question is that do you think it's possible to distinguish like the contribution to this entanglement entropy, whether it comes from the particle number or comes from the energy flux? Intuitively, I think probably like the particle number should count, but not the energy flux.
So this is actually a very good question, and it's something that I haven't fully understood yet. The example that, I mean, interestingly, the example that Fulling and Davis were giving, I think, was the example of uniform acceleration. Because in that case, the state that you measure here in the future null infinity is at 0 temperature. So there's actually no, as you said, there is no, the stress tensor vanishes here. So there's definitely no production of energy radiated to this region. And still there is a production of entropy. They phrased it in terms of particles. I have a slight, I don't fully understand what is the correct notion of particles that one should use in this setup, because if you actually compute the expectation value of the number operator, for example, for the fermion, this vanishes everywhere. It vanishes identically. So I think one is supposed to measure some other quantity, which is something like the content of quasi-particles. And I think there was some of this was discussed in this recent paper by the group from Kyoto. Actually, I prefer to think about it in a different way. I mean, and that is somehow the reason why I was giving this example. So I think here one way of thinking of what is producing the entropy is we don't need to, entropy is being produced because the correlations between the two chiralities are being changed.
Right.
You know, I don't need to resort to some like weird notion of particles to explain this. It's because the modular Hamiltonian of the system is changing, because the quantum correlations between the two different chiralities are changing. They are getting decorrelated. This is exactly what's happening in this example, and that thing is making the entanglement entropies grow. But I think that there is a way to rephrase all of this in terms of quasi-particles. It's just that I don't understand it very well.
Yeah, I think, yeah, this is probably quite interesting question. Maybe we could discuss later.
Yeah, because in this paper by from the Kyoto group, they had this interesting observation that they could sort of define a co-dimension 1 surface where the particle, this quasi-particle production is more or less being created.
Yeah, the peer production.
Yeah.
Mm-hmm.
And I think this picture should also apply in this setup, because what they were saying was universal. I mean, they did it for any CFT. So I think this is a point that definitely deserves to, yeah, understand better.
Mm-hmm. Yeah, thanks. Would anyone else be willing to ask a question?
Okay, so maybe I have a nice question. In this last part on when you were discussing AdS, yeah, well, actually, maybe the slide before. So I because I thought that we can basically for free fermion or something on AdS, we could still use like a replica trick, right? So I could just compute the Renyi entropy by some correlation function of twist operators, and they are primaries, so I know how they transform under Weyl rescaling. So I can compute all the Renyi entropies from the Weyl rescaling. Is there some flack in this argument? And then from once you know all the Renyi entropies, you should be able to get the spectrum and on AdS. So what goes wrong with the argument?
You mean why can't you get the modular Hamiltonian? You mean?
Yeah, on curved background, because you said that.
Very good point. Yeah, I agree with everything what you were saying, except that knowing the entanglement spectrum gives you the modular Hamiltonian, because this goes only one way. So
oh no, but I didn't say that it gives you the modular. It just gives you the eigenvalue, all the eigenvalues. So, but do you actually need the operator or whatever?
Yeah. So what you said is, I think, consistent with this slide. So I can use the replica trick in AdS2. I put confirmed boundary conditions. There's no problem, and you get the spectrum of the reduced density matrix. That I totally agree. That's actually what I did here. But what I wanted to point out is that if you want to compute the density matrix itself, not just the eigenvalues, the operator itself, because I want to do modular flow and maybe, I don't know, do interesting stuff in AdS, I'm not going to be able to obtain it in that way, because although I know the spectrum, I don't know this operator K. It's not giving me the modular operator or the modular flow. So this is a calculation that you need to do from scratch. But if we're just talking about the Renyi entropies, I totally agree. The replica trick does the job.
Okay, sure. I was not careful. I didn't listen carefully.
So I went too quickly through this slide.
Probably we have already enough questions for Ignacio. And yeah, let me take this chance to thank Ignacio again. Thanks for the very nice talk, Ignacio. And hope to see you again next week.
Sure.
I was